Hello everyone, I am George Igwegbe and I am thrilled to be here at Hackster Impact Summit. Today, I will be presenting a project we worked on last year, which involves augmenting digital meters. My presentation is titled Tiny ML Digital Counter for Electric Metering System. This project inspiration originated from a challenge we encountered in our apartments. Specifically, we noticed that our digital electric meter was inconveniently located a considerable distance far from our living space. Our interaction with it were mere limited to occasional need for electric unit payments. There were instances where we ran out of units late at night or during crucial meetings, resulting in an awkward and embarrassing situation. This situation prompted us to contemplate the development of a non-intrusive and seamless integrated solution for our already existing digital meter. As mentioned earlier, I am George, and here is my project partner, Martins. We are both graduate students at Carnegie Mellon University, CMU, specialized in artificial intelligence. Before joining CMU, I worked as a machine learning engineer with a focus on computer vision. On the other hand, Martins worked as an operational excellence lead in a FMCG company. The project outline is straightforward. We begin by collecting data, followed by processing the data, then move to model training, then model deployment, and lastly, I will introduce the dashboard that provides valuable insight into the problem. For a comprehensive understanding of the project, here is the project workflow. Choosing the right device for this project was a bit of a puzzle. We had a wide range of hardware options to consider, each with their own blend of performance, power capability, and features. On one end, we have the popular Arduino BLE-33, packed with 1 megabyte of flash memory, and is also packed with powerful varieties of sensors such as humidity, accelerometer, and color sensor. While on the other end, we have the Raspberry Pi, which is a general purpose Linux machine. For this project, we settled on with the OpenMV camera. This is because of its compact size, decent processing speed, and compatibility with MicroPython, which made it the right choice for the job. So after selecting the hardware, the next step is the data collection phase, which happens to be the most significant phase because it was a bit challenging, given that we have to gather our own data. To address this, we designed a suitable rig capable of holding the OpenMV camera and its powered source. The rig allows for physical adjustment during the initial data capture process, providing protection against tampering, minimizing the impact of wind interference and other sources of error. After then, we develop a calibration and data collection script, specifically captures the digital screen instead of the entire meter. This approach helped us reduce memory usage and also reduce processing demand. Then we move to the data processing phase. So the captured data underwent additional processing using relative coordinates to isolate and segment the digits considering the decimal points. The data collection process yielded a total of 3,000 plus digit data points. We then manually label the data set by individually categorizing and moving the images into folders marked from 0 to 9. Subsequently, a verification step was incorporated during the later stage to address any labeling issues. We then moved to the model training phase. So after the data preprocessing phase, we uploaded the dataset to Edge Impulse Studio, configured the input of our model based on the dataset specification, that is the image width and image height. In this study, we employed two models. The first is a pre-trained model, and the second is a vanilla model. We also specify the output picture of the model which in our case was set to 10 classes. After the pre-trained model was used, the pre-trained model that was used was a MobileNet B2. We decided to leverage on the power of transfer learning. However, it did not perform well. So we decided to train a vanilla model from scratch using our data set. We built a neural network consisting of 3 layers and trained for about 200 epochs with a learning rate of 0.0005. Then, as previously outlined, the MobileNet performed poorly in both F1 and accuracy metrics, while the vanilla model excelled. Upon conducting an in-depth investigation, it became evident that the limitations were primarily rooted in the use of the MobileNet as a foundational model for training. MobileNet is optimized for input size 96 by 96 or 160 by 160 in order to achieve optimal performance. However, our input data deviated from the norm. It had a dimension of 15 by 20. As a result, we made a strategic decision to move to the vanilla model. We trained it with the same hyperparameter. This adjustment led to a significant improvement in our results. Then we moved to the deployment phase. Upon completion of the model training, we opt for a quantized version due to OpenMV's exclusive support for int8 model, as opposed to float32 model used during training. The figure we have shows that the model size was compressed by a factor of 4, serving as a compiling example for TinyML's remarkable capability. Then the deployment phase. Because the metering device was situated in a separate location from the apartment, a Wi-Fi range extender was installed to facilitate internet connection for the OpenMV Wi-Fi shield. In essence, the OpenMV device, which hosts model, handles the computation and transmits real-time data via MQTT protocol to a dashboard. In our case, we did use Adafruit's.io dashboard. This enabled immediate updates on pending credit points in the meter. So while we have successfully completed this project, we intentionally omitted certain features to maintain simplicity. Nevertheless, we are confident that the project can be expanded to enhance system robustness. First, we propose the incorporation of nighttime data capture and inference. This may require integration of light-dependent resistors, LDR, and infrared bulbs to enable data capture and inference during nighttime hours. Second aspect involves the development of more robust and efficient method for identifying the region of interest. In our case, we had coded the region of interest, but we believe that a more sophisticated approach can enable us to accurately determine and locate the region of interest. So finally, I would like to thank you for your attention, and I would like to express my gratitude to Hackster for the invitation. Thank you.
Today, I'm going to talk about one of my projects, surface crack detection and localization. So before that, a brief self-introduction. So about my day job, so I studied information technology, computer science, and bioinformatics. Currently, I'm working as a researcher at RIKEN, which is a top-notch research institute in Japan since 2007. And I have been mostly doing the microbial genome sequencing data analysis in my day job. But I also have a side gig as a hobby job, and I have started blinking an LED on an Arduino Uno and experimenting with Raspberry Pi in 2013. And it was all started from there. And I am an active project contributor at Hackster.io, Electromaker.io, and Hackaday. And I have won more than 10 awards in various contests since 2020. Now, also, I'm one of the winners of the Google TensorFlow Liteform Microcontroller Challenge in 2021. And most of my projects are related to the machine learning at edge devices. So the purpose and scope of this project, so it is in last year, in Pitt's work, a 50-year-old bridge collapsed. And there was only one reason why a sturdy structure such a concrete bridge could suddenly collapse. So that is wear and tear. And concrete structures generally start deteriorating after about 40 to 50 years. And overlooking signs of wear can result in severe accidents. That's why the inspection and repair of the concrete structure are crucial. So the conventional method of typically a specialist would inspect such kind of a structure by checking for checks visually and sketching the result of the inspection. And they prepare the inspection data based on the finding. And this kind of inspection method is not only very time consuming, tedious, and also very expensive. And it also cannot accurately detect the cracks. So in this project, actually, I have built a surface crack detection application using machine learning. A pre-trained image classification model is fine-tuned using the transfer learning with the Edge Impulse Studio and deployed to the C terminal, which is based on Raspberry Pi Compute Module 4 that detects surface cracks in real time and also localize them. So why localization? Why do we want to localize the detection using an image classification model? Cannot we use the object detection model itself? So of course we can use the object detection model, but we would need to add bounding boxes to thousands of samples manually. And also we can use the existing object detection model, but may not be a good choice to auto-annotate these cracks since they are trained on definite shape objects. And repurposing the classification model for localizing the detection saves a lot of time and effort and still would be able to identify the region of interest. So how does it work? So the CNN, the convolutional neural networks with GAP, that is the global average pooling layers, that have been trained for a classification task can also be used for object localization. So that is GAP CNN not only tells us what object is contained in the image, it also tells us where the object is in the image, and through no additional work on our part. And localization is expressed as a heat map, and where the color coding scheme identify the regions that are relatively important for the GAP CNN layers to perform the object identification task. So before doing the model training, we need to collect the data. So the data set were downloaded from the Mendeley data, that is concrete crack images for classification data sets. And that data set is divided into negative and positive crack images for image classification. And each class has around 20,000 images with a total of 40,000 RBG images with 227 by 227 pixels of resolution. And also to differentiate the crack and non-crack surface images from the other natural world scenes, we have mixed around 25,000 randomly sampled images from the COCO mini train, which is a subset of the COCO train 2017 dataset. And these collected or downloaded images are labeled into 3 classes actually, and saved into the directory with the label positive, negative, and unknown. And the data is uploaded to the Edge Impulse Studio using the Edge Impulse CLI. And for the model creation and training, so first we have to actually design an impulse in the Edge Impulse Studio. So designing an impulse is actually you define what is the image sizes and pre-processing pipelines and what kind of model you are going to use. So in this case, we are using the transfer learning images. And for the model creation, we are using actually the MobileNet V2 160 by 160 transfer learning model with the pre-trained weight provided by the Edge Impulse Studio. And the pre-trained model outputs the class prediction probabilities. And to get the class activity map, that is the through which we will be generating the heat map, we needed to modify the model and make it multi-output model. So to customize the model, we need to switch to the Keras mod in the Edge Impulse Studio, where we can actually edit the model and customize. So you can see the model, final model, bottom layers in the image on the right side. And after the model training, so actually model was trained quite nicely, and we have the, for the quantized model, the accuracy is above 99%. And for the model deployment, currently Edge Impulse for Linux SDK does not support a multi-output model. So we will be using the compiled TensorFlow Lite runtime for inferencing. And to accelerate the inferencing, the TF Lite interpreter is used with XNNPAC, which is a highly optimized library of neural network inference operations for ARM devices and other platforms. And this application actually uses multi-threading to use all available 4-core on the Raspberry Pi 4 compute module to achieve low latency and better and higher FPS. So this is the application workflow. So we have actually the one task or one thread is actually capturing the images from the camera. And another task or thread is actually displaying the result to the LCD screen. And there are two queue, which is maintaining the incoming and outgoing data. And the two threads is actually doing the model inferencing. So we are using up total 4 threads here. So the heat map is actually overlaid with the input images whenever a crack is detected. And you can see the sum of the test run results images on the left side, on the right side are given here. And this is the live inferencing demo. So I have actually recorded this.
Hello guys, so we are going to demonstrate the inferencing. So we are under the bridge. So this is the railway bridge, and we are going to detect cracks under this pillar. So the returnal is already mounted on tripod, and there is a Raspberry Pi camera, which is other side of the returnal, and that is connected to the returnal over the ribbon cable. And so let me start the app first. So app is started and it is pointed to the crack and it is detected crack. So if you want to overlay the heat map, so you have to click on the F1 button and it can correctly overlay the red color on the top of the crack. So this is doing the inferencing correctly. Thanks for watching.
So the conclusion is this project showcases an industrial use case for the surface crack detection that can be used for the predictive maintenance. And the project has the following key characteristics. So we can actually customize the pre-trained transfer learning model, and we can use the runtime heatmap visualization to localize the detected cracks. And this is a multi-threaded application to increase the frame rate. And this is a very much scalable and portable device. And next step in future work would be we can use a drone to detect crack on the tall concrete structure. And to achieve the faster FPS on high resolution images, we can use the latest Raspberry Pi 5. So that's the next steps. Thank you for your attention.
Hello, my name is Constantin, and I'm the founder of Zalmotech, a company that started as a group of makers offering IoT services that evolved to one focusing on computing on the edge solutions tailored to the client's needs. Our project, called Predictive Maintenance with Tiny Automator, posted on Hackster a while ago, focuses on an industrial case study. The concept could be used in many other smart city scenarios where a decision on the edge would be more efficient than a round trip to the cloud and back. But let's take a step back and see what the initial challenge was all about. Our client needed to monitor large-scale production lines, extruding plastic to create pipes. These production lines usually have a large motor in charge of pushing the material inside the heating element. This motor, as you can guess, is critical to the functioning of the whole production line. Any downtime could pose serious problems to the factory in case of machinery failure. The motor had only basic information gathered into its default PLC, like current draw, that does not tell you the whole story. We had a task to gather important vibration and temperature data in real time from the motor and create a machine learning model that understands what normal functioning parameters are and treat anything that goes beyond these parameters as an anomaly that is either stored locally or reported to a dashboard where the plant manager can take action if necessary. For the machine learning model, we have used the Edge Impulse platform, where we uploaded raw data of what the factory confirmed are normal values for the machinery, and created a model that we deployed on an industrial-grade Raspberry Pi system, where, based on the rules engine, creates appropriate actions at all times. The Edge Impulse platform allows any maker to freely create machine learning models on a large number of supported hardware platforms and deploy them easily to work either offline or sending alerts forward to the cloud if needed. The Edge Impulse platform allows any maker to freely create machine learning models on a large number of supported hardware platforms and deploy them easily to work either offline or connected to cloud solutions for more complex business logic. The really impressive part of this solution is that you can train it directly on the machinery in real conditions that are specific to the location, part created, and power cycles. If any of these conditions change, you can retrain it remotely after installation. Next, my colleague from Waylay, Ramil, will give an overview of the architecture and potential that Tiny Automator offers and how it could enhance your upcoming Smart City project.
Hi, my name is Ramil Israfilov, and I am a senior software developer at Waylay. Today I would like to give a brief overview of our Edge solution, which is named Waylay Tiny Automator. Maybe first short introduction to Waylay itself. Waylay is a software company that provides a low-code hyper-automation software platform. So back to Tiny Automator. So Tiny Automator, it is a Waylay's Edge solution. So it's primarily focusing on edge automation. It also stores and visualizes data locally. It provides the ability to run automation scenarios and can run machine learning models locally. Waylay Automator, Tiny Automator is composed of a few Docker images that include the Waylay console, Waylay rules engine, resource service, which is a digital twin service, time series database, an embedded sandbox VM based on Node.js. So the latest Tiny Automator includes also alarms service that can be used to trigger and monitor alarms based on the threshold rules in your automation scenarios. Inside Tiny Automator, you have a data injection layer, which is using Mosquitto MQTT broker. And the data which is coming via MQTT then pushed towards our Waylay broker servers and stored on a time series database, which is based on InfluxDB. Let me do a short walkthrough over Waylay Tiny Automator. So here I am on a Waylay console. Here, first, as I mentioned, you can configure your data ingestion layer based on MQTT broker. Once a message is arrived, you should be able to see the data on the digital twin, we name it a resource, created on a Waylay platform. So here it is one of HVAC systems. Here you see the incoming data and also the metrics which are stored on Influx database, and here so on time series database, and here you actually can also see visually the evolution of that metric data. And the core of a Tiny Automator and a Waylay platform also is a rules engine, which consists of plugins, or we name sensors, which is a software-defined sensors or Lambda functions. They consist of input parameters and the Lambda function code, and they produce state and raw data upon execution. The automation rules are created using Visual Designer. And business workflows, we name them templates, are created by just drag and dropping the plugins, sensors from predefined library. But you can also extend that library with your own plugins because it's just a JavaScript function. There is a plugins SDK available for that. And you wire the required sensor execution using transition, and also you can split your execution into subtrees and merge them back using logical gates. Once a template is defined, you can invoke those templates using tasks definitions, and those tasks actually will be running based on incoming data on a resource which is associated with that task, or they could be also running on periodical basis. And on that demo setup, we have a couple of use cases running. One of them is car parking occupancy detection use case, where we take pictures using a webcam on periodic pages, and once that image file is saved, we push a message towards Tiny Automator to invoke that task. And the task does image classification using a machine learning model. So in that case, it's using TensorFlow.js, but it also could use an Edge Impulse machine learning model. Once classification is done, we, as a next step, we calculate number of cars based on that classification result and store that message on time series database for further processing or visualization. So for example, here we can see some data, current data on that parking. So here we also sent some visualization data or classification result if it is classified. So here you see that, okay, there is a car detected on a parking with probability of 55%. That's all that I wanted to share during that short session. So if you want to try it yourself, you can go to our website to Edge Solution part and install it using our installation guidelines on a device of your choice. We also shared some demo projects on Hackster.io platform. You can find them using Tiny Automator keyword. And I hope you can get some inspiration on your future projects.
Hello, everyone. Welcome to the 2023 Hackster Impact Summit, and welcome to my presentation, Pothole Detection with Sony's Presence. My name is Justin Lutz, and I will be your presenter for this session. Before we get to the project, a little bit about me. So I got my bachelor's degree in computer science, and for the first 8 years of my career, I was a software engineer at Raytheon, which is a US defense contractor. In that time frame, I also got my MBA, my master's in business administration, part-time, while I continued to work full-time. I recently retired as a member of the US Military Reserves. I did 22 years between the Navy and the US Marine Corps, and just retired in February of 2023. I started getting into hobby projects in earnest in 2021. I'd always wanted to try out Arduinos and Raspberry Pis, but never really got around to it. Finally took the time to start doing that in 2021. And that got me really excited about Edge AI and IoT. It was just starting to become popular. Models were getting to the size where they can be put on constrained devices such as microcontrollers. And that got me really excited about the capability of having models right at the edge, right next to the sensor. We could do inference there rather than sending the data over to some data center to do to run the model there. So really exciting time. So I did a bunch of projects, put them on Hackster, entered a couple contests. It was a lot of fun. That caught the eye of a couple organizations, notably Edge Impulse, which many of you may be familiar with. They have a really great framework for building and deploying models for the edge, as well as Blues. they have a note card and note carrier hardware to really make it easy to for the IoT space. So I joined the Expert Network for Edge Impulse in 2022 and the Blues Amplifier program in 2023. And it's been a really great experience learning to use their tools, use their hardware, and build projects off of those. As I mentioned earlier, I've been with Raytheon for a while now. I started in software, and now I'm a quality leader within their naval power organization. My family and I live in Massachusetts, where for those of you outside the US that aren't familiar, it's in the Northeast United States along the Atlantic Ocean. And in the bottom right is a photo of my wife and 3 children at a recent Halloween event. Halloween is a pretty big holiday around the Massachusetts area due to the history of the state. So we try to soak it up and have fun. All right, now on to the project. So as I'd mentioned, I live in the Northeast United States and we experience all kinds of weather. We have cold, snowy, and icy winters. We have hot and humid summers. We have rainy springs and cool falls. So all those temperature changes can cause damage to our roads due to that expansion and contraction of the groundwater in combination with heavy vehicles driving on the roads. And it's not a trivial issue. Each year, potholes can cause over $3 billion in US dollars in damage each year, according to AAA. And that's due to not only damage to the vehicle, but time lost due to traffic as a result of the damaged vehicle, lost time due to waiting for a tow truck to bring to a garage to get fixed. And then there's the time that it takes to identify the pothole, notify the correct people about the issue, and then repair the pothole. So within that time frame, multiple cars could get damaged from that pothole. And then at the extreme end, there's also the potential for injuries or death due to the potholes and driving at high speeds. So my solution was to develop an automated pothole detection hardware and software solution. So the intent was to use a computer vision model to identify the pothole, use GPS coordinates to locate where the pothole is, notify the appropriate people. In my case, in my area, that's the Department of Public Works that's responsible for fixing the roads in our area. So notify them immediately with an LTE connection. And to do it passively, right? We don't want to introduce more vehicles onto the road to collect this data. So we can use previously existing infrastructure like garbage trucks and mail carriers that do daily runs on the roads anyways. So why not just mount that hardware onto those vehicles to passively collect the data? And then, of course, you want to save the photos to an SD card as well for validation. You want to make sure that your model is running appropriately. So if the model detects a pothole, just snap an image of that frame and save it to an SD card. So at a later time, you can investigate to make sure that the model is acting appropriately. And if not, you can add that new data to the model and retrain it. So for my implementation, I used Sony Spresence hardware, not only the Sony Spresence, but the LTE extension board and the camera board as well. And I also printed a 3D enclosure on my 3D printer to keep the hardware safe. So the camera is obviously to take a photo. Great thing about the Spresence is it has built-in GPS. So I didn't have to add an external GPS. I could use what was already on the hardware. And then I used the LTE extension board to transmit the coordinates of the pothole. To build my model, I used a Kaggle dataset. So that had various photos of potholes and clear roads. And I used my own data as well from trips that I took around my local roads. And I imported that all into Edge Impulse. So for Edge Impulse, I used that data to create the model. I used a simple image classification model using MobileNet and then did transfer learning off of that. And then Edge Impulse does a great job of deploying the model as well. So I could use that to import it as an Arduino library into the Arduino IDE and then build my code off of that. And then finally, I used the AWS IoT core for MQTT messaging. So I could send the coordinates of the pothole to the appropriate location. At the bottom, you can see a photo of the hardware. And then on the bottom right, you can see some of the tools within the Edge Impulse framework. So what can we do in the future? So I see two areas where I can improve the project that I worked on. First off is implementing a better model. So in the example that I used for my project, I used grayscale imaging, and I got about 80% accuracy using that model. And I think if I'd used color photos, 3-channel instead of grayscale, which is 1 channel, I would have gotten better results and possibly a higher accuracy. So that's one area that I'd like to explore. The Spresence has enough memory where I'm able to accommodate a larger model size for a color-based model. And then the second piece is using object detection, which uses bounding boxes instead of just a binary image classification of pothole versus no pothole. So as models get more capable and smaller, they can fit on smaller and smaller microcontrollers. So that's a future capability that I think could be explored. The second piece is just using more powerful hardware. So instead of using a microcontroller, use a single board computer. So I have 2 examples here. I have NVIDIA Jetson Nano. They also have the Orin, which just came out recently, which is also a very capable single board computer. And then in the bottom right is a Raspberry Pi 5, which was just released, I think, a couple weeks ago. So as hardware gets more capable, that means you could run more complex models at the edge as well. And I don't think it introduces any difficulties in terms of powering it. You can still use a 12-volt socket within a vehicle. For my project, I used a battery. But for those higher powered, more capable single board computers, I would recommend running off a dedicated power supply. Or, as the expression goes, the best defense is a good offense, or the best offense is a good defense. Prevent potholes from even happening in the first place. So that way you're not reacting to potholes being formed and trying to repair them as quick as possible. Why not just develop a type of asphalt that is self-healing? So researchers are actually looking into that right now. I saw an example in Oklahoma where there's a stretch of road where they implemented this self-healing asphalt, and they're getting great results. So that's more addressing the root cause, where you're preventing potholes from happening in the first place, so you don't have to spend all this time developing models to detect potholes in the first place. So that's for those of you that are interested in material science and stuff like that, you can do some research there. That's some really interesting technology that they're looking into. So that's my presentation. Thank you for tuning in. You can follow all my projects on Hackster. That's where I post them. So you can reach out for any questions or comments there. And I believe there's a Discord channel as well during the presentation where you can ask questions there as well. And I'll tune in and try to answer as best as I can. So thank you and have a great day.
Hi everyone, today I will talk about my IoT project, my IoT air station detecting air pollutants and providing IoT surveillance. I am a self-taught full stack developer and Edge Impulse ambassador, maker, and independent researcher. First of all, why did I decide to focus on creating an AI-based solution for air pollutants in urban environments? First of all, I started to detect the issue and create a map for how I can develop my solution. First, the issue is mild air pollutants like nitric oxide can react with each other and evolve into more dangerous contaminants, spreading very rapidly in the environment. And they create noxious air contaminants, and these contaminants pervade ecosystem very rapidly and engender climate change, poison wildlife, and impact the respiratory system detrimentally. Nitric oxide, the most common form of nitrogen, mostly generated by forests and nearby living animals, is rapidly oxidized in the air to form nitrogen dioxide, one of the most hazardous pollutants. And nitrogen dioxide can be created by any available oxidants in the area, oxygen, ozone, or volatile organic compounds. As a primary air pollutant, nitrogen dioxide causes a range of harmful effects on the respiratory system, increased inflammation of the airways, reduced lung function, increased asthma attacks, and cardiovascular harm. Road traffic, urban sprawl, and thermal plants, mostly coal-fired, are considered the principal outdoor sources of nitrogen dioxide. Therefore, densely populated and industrial cities are most vulnerable to its detrimental effects. For instance, I live in Bursa, Turkey, and it always comes in first or second pollutant city in Turkey for air pollution, because it's an industrial city and most of these pollutants are caused by the nearby thermal plants near the city. Since tall structures, buildings change air currents depending on the landscape and terrain, poor urban planning multiplies and boosts the effects of pollutants by encapsulating them and not letting them to go to higher altitudes. Then after defining the problem, I started to create my own solution. First of all, I decided to detect reactive gas surges leading to chemical reactions creating noxious air contaminants such as ozone and nitrogen compounds. Since photochemical oxidant reactions creating these noxious pollutants are inextricably related to airflow, heat, humidity, and sunlight, generating a local data set showing these parameters in a local area is crucial to get precise predictions for air pollution locally. Then train a neural model with notable validity by utilizing the local dataset to get predictions. Inform the user of the model detection results immediately after running an inference with the model to let the people take precautions to avoid the harmful effects of the air pollutants. Since this is still as explained earlier, the poor urban planning can boost the air pollution effects. Providing a real-time surveillance footage for further examination of the local area will help preclude perilous pollution effects depending on the layout. Since this prototype will work outdoors, considering harsh operating conditions, designing a 3D printable case to make the air station as robust and compact as possible also important. As you can see, I shared my design files here and show my prototype. You can find the 3D printing files, STL files on the tutorial page and create your own prototype to install anywhere. After deciding my solution process, I started to build my prototype. First of all, I construct a dataset with notable validity. I programmed Arduino Nano to collect air quality data via DF-robot electrochemical gas sensors, a DF-robot anemometer kit, and a DHT32 sensor. I utilize Arduino Mega because Firebeetle ESP32 can generate library inconsistencies on Arduino IDE for the gas sensors. Then I assigned air pollution classes for the collected data records, clean, risky, or unhealthy, depending on the official local air quality index estimations. I show my local area air quality index estimations, and you can find yours on probably your government's page, government's climate department page. I utilize 3D control buttons connected to Arduino Mega to select an air quality class, to assign a class to collect data record. Then I programmed Firebeetle ESP32 to obtain the collected data parameters via serial communication and save the retrieved information to a CSV file on the SD card. I collected these data parameters: nitrogen dioxide concentration, ozone concentration, temperature, humidity, and wind speed as my parameters. After creating my datasets, I started to build my neural network model with edge impulse. After scanning and pre-processing all my data records on the SD card, I uploaded them to the edge impulse, but you do not need to take this step now because edge impulse provides a CSV wizard to automatically pre-process all of your data records, even if it's a single file CSV data. Then I designed and trained my model on the given air pollution levels, clean, risky, and unhealthy. Then I evaluated the trained model accuracy, deployed the validated model as an Arduino library, and set the deployed model on Fireball ESP32. After that, I utilized Fireball ESP32 to capture surveillance footage after running an inference model and transfer the detection results with the captured image to the web application directly. Then, to inform the user of the detection results with real-time surveillance footage, I decided to develop a full-fledged web application in PHP, HTML, and JavaScript. I hosted my web application on a LAMP server on LATAP Delta, but you can utilize any server you want to host this web application. I also shared all the files related to the web application on the tutorial page. Mostly, I employed web application to obtain the model detection results to collect air quality data. This means the models use data parameters to estimate the air pollution level. I also get the data record on the web application to create a more precise lookout for the real solution, and to capture surveillance footage from Fireball ESP32 via an HTTP POST request. After receiving a data packet via POST request, the web application converts the received raw image data to a JPEG file via Python script, since Fireball cannot generate a JPEG or PNG file. Then the web application updates its homepage or interface automatically to display the latest results with the received surveillance footage. Therefore, the web application lets the user to get information without giving any comment or refreshing the web application page. So after opening the web application's homepage, you can get any risky or unhealthy situations related to air pollution automatically. Then further discussions on the next iteration. As it is now, installing this prototype and running it on your local region can prevent human-made air pollutants from harming the respiratory system, reduce the risk of increased asthma attacks and cardiovascular harm, as a person experiencing asthma attacks, by utilizing a device like this can provide me more insights to not go outside in a dangerous or harmful air pollution risk, and also help to avoid a potential asthma attacks. Then by installing a device like this can protect people with lung diseases from severe symptoms of air pollution, especially for elderly and children. It can also benefit them, and provide precise warnings regarding a certain photochemical oxidant reactions and transmission rate. After this prototype and my first device design, I decided to create a second iteration and make some improvements. I want to create a new device with LoRa enabled and GPS enabled with a smaller and more compact case. It will let the user to place multiple units in a single local area and get more data points from the running models, and send this multiple units data to a hub, to a main server operating as a hive mind. After getting these detection results from multiple units, the device will run a second regression model to generate more precise location, not even for the placed local region, but also the adjacent local regions, can provide insights for the adjacent local regions to prevent air pollution. And getting diverse surveillance footage from multiple units can easily let the users to track the degradation of the urban environment. Thanks for listening. You can get all files and coding instructions from my Hackster page. Also, if you have any further questions and watching this later, you can reach me on my social media. Thanks for watching.